Well, thank you. My brain is so full, and it's always hard to give talks where you tend to be overreactive to amazing things that you hear. But I actually want to thank the speakers for giving me all kinds of good ideas, and for Bob for including me in this, because this is not my usual crew. I, like Jerry Vitek, run a DBS group on depression. And now I've just moved to New York, and this is my old team, and I'm going to try to use some examples from this because I think that we want to use the opportunity to talk about what are the challenges in studying mood disorders, because we've been talking about things where you have real pathology, real cell type abnormalities, real concrete stuff to deal with, and now we're really in the field of fuzzy. And the question is, I want to convince you that fuzzy is good and fuzzy is quantifiable, and that depression actually can be looked at and treated and thought about and modeled, and is certainly the ultimate disorder where non-human primates is not just a good idea, it's really essential. So what are the challenges in depression? I mean, I think we struggle, and just for disclosure, I'm a neurologist by training, so I'm not a psychiatrist because I don't like fuzzy. But in fact, you can deal with the fact that there is an experience that we're trying to model. And so we want to know what it is, what we're treating, and how it's measured. And if you read what a first-person perspective is for a depressed person, and since it is very common, many of you may have had the experience, it is a physical state that involves intense negative mood, an absence of positive, and in many ways, as William Styron defined his own experience, as a gnawing agony, a pain, a self-loathing that really drains your energy and your attention and actually makes it so that you feel immobile. And when you think about it, the idea, it's a very unnatural state to not be able to move away from pain. And that is the nth degree of a bad depression. But I think we can kind of deconstruct that and basically say, which neurologists do, you have an emotional state with problems with motivation, intention, and action. We've listened to that for 2 days. So what might recovery look like? That you can move, that you'd be without pain, that you feel like your old self. All these things are things that patients talk about. They don't really want to be happy. They want to be energetic and without pain. And the question is in what order should these kinds of symptoms change, and what pieces of them can you model in a non-human primate? And again, I put this back in because this is my Bible. I've got Peter and Jerry as a substitute for Malin DeLong was here. I mean, I was around when they did those monkeys at Hopkins too and saw them. Except I was interested in limbic circuits in this, and those were part of our original models back in the early 80s. And I think, again, it just lends itself that non-human primates is at the core of all of this human work, and it's really guided all of the work in the field. So what are the limitations of the status quo? I mean, how do you make a diagnosis of depression? Well, it's kind of like a Chinese family menu. You have either high negative mood with or without anhedonia, low positive. You can actually have low positive without high negative, which is sort of twisted in my mind. But then you have 5 out of the 8 combination of abnormalities in drive, attention, energy. And then there's weird stuff that you're never going to be able to model, like guilt. And I don't know if monkeys commit suicide, even though I've heard about monkeys that may do self-injurious things. And treatments are available, but one size doesn't fit all. They come in all flavors, all classes. You can do talk therapy, you can do different classes of drugs, you can give shocks. But I want to kind of spend the rest of the time to talk about the idea that if you have a brain model and you deconstruct and try to simplify but put the symptoms into quasi-components, that actually you set up how you could do focal neuromodulation to actually move and drive the system, whether it's with optogenetics or it's with, an implant. And that's certainly, actually, I'm sure I'm doing here. Well, I have a job now. All of the foundation for it was from Parkinson's disease, but only was possible because there was imaging. So again, to have Dr. Van Essen give that magnificent multimodal imaging talk, I mean, without that kind of work, without the technology, and without kind of being in the draft of Parkinson's disease, you wouldn't kind of think to do this. So like Mar Sanchez talked about yesterday, you can think about a depressive episode, and we're really reverse engineering to the brain. And that you have some mood regulatory circuits that you may be able to model, but that there's biological vulnerability and stressors. They're all interacting. I'm cutting straight to the chase. When you're in a depressive episode, what does it look like at the level of the brain? What happens when you treat that state and use the change model as a probe to just actually look at what blobs in the brain change? If you go back to 1986, when we started doing this stuff, it's embarrassing what these blobs look like. I mean, with all due respect to cell-specific tract tracing, we have big blobs. We've looked to see how it evolves, but if you look for common patterns, you can reach a point where actually, as we did, that we honed in on the fact that Area 25, you're going to hear about this hopefully from Angela Roberts in her talk, is seeming to be a common node. And its interaction, its functional connectivity with prefrontal cortex, and its structural connectivity with many other areas, and I didn't read the Bible, I read tract tracing from non-human primates to understand what should Area 25 be doing to what other areas. And at the time, with movement disorder, it was depolarization block and activity. We wanted to block Area 25, get disinhibition of anything it was talking to, and we would re-regulate people who were stuck sad. And that was the logic. And you can read the papers because there's not enough time. But that basically, if you stimulated at high frequency, you could immediately turn negative off, and people could attend, felt like moving, and that you could maintain that state with chronic stim over time. You did have people who didn't respond. You did have changes with overactive 25, actually downregulating its metabolism, so it behaved as kind of hypothesized. And with subsequent studies, there is this chronic effect with recovery. Like most antidepressants, don't happen immediately. It takes time. And this was replicated in different groups of patients. And we can discuss whether there are more no coffee breaks, when it doesn't go exactly right, because people had other logic. Maybe we ought to push positive. Maybe we want to stimulate. Maybe we ought to deal with negative prediction error. People have looked at the habenula. People have looked in the ventral striatum. My attitude is, if you have pain and you can't move, get rid of the pain, make your own happy. And that's our choice, our logic, and how to model that we had a place we wanted to go. But it became very clear that everyone didn't get better. You need more precision in terms of where. You need to know who is the right person. Maybe different patients need different treatments. You need to know what is the trajectory of recovery? What are the parameters? What actually is the mechanism of something we're doing? And I think that this is why this group and non-human primate researchers in general, this is the point that we need your help. Because I've got an electrode in people and I can get them well and I can keep them well. I have people 12 years that were ECT failures that now have a pacemaker. They go about their business. They have good and bad days, but they don't go back into that hole and can't get out. The question is, what do we do to them? We can't wire up everybody in every place. The most person with electrodes in your brain wins. You've got these crazy new devices that no one knows how to use and that may not work very well and aren't supported. That what we need are ways to have better maps, understand the time course, have causal models, and actually move it, reverse translate it to actually figure out what we're doing so that maybe we could do it without an electrode at all. So the strategy that we took was to do it, to first figure out the where. because I can't fix psychiatry. I can't come up with a biomarker of the right patient any more than you all can kind of argue about what's the best causal model, but that the clues were there from the imaging and the patient studies. The surgeon didn't miss. We just didn't understand what the target was, because just like you all, you just don't do something locally to some cells. You do something to those cells and everything that they talk to. And it turns out that we aren't actually stimulating area 25 directly at all. It's actually we're stimulating the white matter. And so what we did is we used our failures. We used people first to say, what did we do consistently? We did tractography, and I know that tractography is not ground truth, and we're going to hear why not from Peter Strick. But what you can do is to see imaging as a biomarker in this setting is to say, can I model with computer science models what I'm hitting in the tracks, and what am I doing alike in everybody? And you can actually determine that you're hitting the cingulum bundle, the forceps minor, the tracks down to the accumbens and the raphe, and the PAG, and that you can then say, what did I miss in people who aren't well? And you can start to model and make adjustments and show that with 1 millimeter difference in where you are is the difference between being partly better and fully better. And now we have a template. So instead of a spot, we have a 4-bundle template. We can drive in an individual person. We can map out that map in an individual, tell the surgeon, put the second contact on the electrode right there, and we can predict that people get better. And the better we've gotten at that tractography guidance, the better we've gotten with high-resolution imaging, the better we've gotten with multimodal imaging, we've started to see an emergent property of what we do. We get a very rapid effect in the operating room, and we have actually a 2-phase to recovery. And we can see it in PET scanning that we have an effect. We reset area 25. It carries over even a month after surgery, and it never changes after that. We reset it. And then we remodel prefrontal cortex, posterior cingulate, the rest of the network at multiple transsynaptic nodes changes over time. And so we now need to have models that actually take into account that we seem to be in a local minimum. We pop out with the first injection of current, and then we have some kind of plasticity not otherwise specified. And we now have to set up models to let us do that. In a rodent, people have looked at how dendrites regrow, or how inflammatory changes change, or how things remyelinate, and how high-frequency stim may actually directly impact oligos. That's something we could do in monkeys. But in people, we start to do the kind of things that we saw Andy and Richard talk about. What are our readouts of behavior? And wire people up, strap it on, put it in them. Whatever you can do to make these measures over time is what we want to do. And as the devices change, we can build causal models. We can look for control signals, and we can track over time. So we can work with computational experts. We can work with EEG. We can make measurements off the device directly. But we don't have the kind of causal control that you have in animals. And here's an example. You're going to hear from Angela about her marmosets and how you can have an excitatory driver of area 25. And she'll talk about her work. But we can see that you can see it with mood induction, tryptophan depletion, typhoid and inflammatory injections, cortisol. There are various models that you can do in monkeys to drive area 25. You can do optogenetic control with opsins and infralimbic. And now that I've learned that we could probably do it in monkeys, so I'm thrilled. So we'll fight between, do we do Angela's model, or do we do the optogenetic model? We've got readouts in the OR electrophysiologically, and we're starting to get a signal of what the reset is by studying what happens every time you stimulate, or looking what happens as a net effect over the time in the operating room. We can do ERP off the cortical surface. We don't have to have 1 million electrodes in the brain, but we can get a reproducible 100 millisecond sweep on ERP with a 2 Hertz ping in the right place that we can distinguish from the wrong place in individuals over time, over a year, every time they come and know we're in the right place. That may help us to get a dose. That may help us to set up a model. That may help you to know what we care about. And again, here's where the translational synergies are. In humans, we now have examples in epilepsy. Put in as many stereo wires as you need and take the opportunity for a week to record from the brain and model behaviors of your choice. And there are interesting things on mood that were published by Eddie Chang's group in the last month. You can take the approach of movement disorder and saying, use tractography to put invasive recording devices on the brain and do it over time and look for coupling features and track physiology over time. Or as Peter Rudebeck and the group at Sinai are doing, use tractography to define these multi-node networks, put in these chronic multiplex recording arrays, and actually let the data show you over time what's happening with causal models as he's doing with reward and anticipation. I just want to end by saying that you want to have kind of other kinds of readouts. So there's brain readouts, there's the rating scale readouts, which are old news. But as we saw in the last talk, we need to have many kinds of behavioral readouts that don't involve self-report. Peter Strick is going to talk about his work that looks at autonomic and body and somatic state interactions. And there's a fascinating overlap between his work and our work, and even us tracking sympathetic drive when we're in the right place or not that maps right into his areas. And we can also be looking and using what we can see in people, whether it's in monkeys or it's in people, that when people are ill, you can see it. You don't need language, you don't need questions, and that one can model that. One can know the neuroanatomy of muscles of facial expression. There's overlap between non-human primates and people. It all converges in Peter's area in the mid-cingulate and the face SMA, and that one can start to take non-models of the face and do machine learning to actually track changes in facial expression as you're stimulating over time. And it really helped me to hear Andy Schwartz's talk about these kinds of models, because it's going well for us. To end, I think the role of complementary non-human primate work is there's all kinds of things we can do with connectome, multimodal, optogenetics, and get quite creative. There are now technologies where you can steer a lead and direct traffic where you want with current in humans. You can have multi-array readouts, but I don't want them for my patients. We can do movement dynamics or posture or voice. The bottom line is we want to line up our tools so that you know what kind of things we're finding has traction. You can model it and help us. And we can have not just forward translation, we can have reverse translation and bidirectional translation, so we help each other toward the common goal of helping sick people. And I'll stop there.
Thank you.